Troy.
When we were doing Biot's experiment,
Yes.
the magnetized needle, like that he had in the stand, could he move it from along the desk? Could he move that needle? Or?
Yes. Okay, so we're going to pick up with the magnetic pendulum experiment that I started to describe for you this morning. And, well, this is the general topic, Ampere's electrodynamics, but I'm actually taking a slight detour to describe what is an experiment done by a colleague of his, Biot, and Biot wants to figure out the dependence of this magnetic force that's coming from the wire with the current in it, the dependence of that force on distance and on the magnitude of the current. And he has the idea from Coulomb that he can use a magnetic pendulum in order to do this. And the setup is really simple. All he needs is, say, a vertical wire, and let's say, he's got a little hole in his desk through which the wire goes, and we'll go ahead and imagine that the current is going up here. And then if he puts a magnetized needle oriented into the board, so that means its north pole is in and south pole is out, it will line up that way, right, just because there's a magnetic field, a magnetic force on it from the current in this wire. You point your thumb in the direction of the current and your fingers go into the board, okay? So that will hold that magnetized needle in that direction into the board. Ben?
The I next to the...
Oh, that's just the symbol for current.
Oh, it is?
Remember? I know it's not very intuitive. You think it should be C or something, but they typically, physicists use I to stand for current. So that just means there's a current in this wire. Okay, now, so he's got this magnetized needle on this pivot, and he can just tweak it, right, in a direction it doesn't want to go, say, and then it'll swing back and forth, just like any pendulum will. And what you see, if you remember when I covered Coulomb, we went through the mathematical argument that where Coulomb showed that if the strength of the force acting on the pendulum is proportional to 1 over r squared. In other words, the force drops off with distance, but it does so as the square of the distance. So if you double the distance, the force goes down by a factor of 4. Okay? If we had that kind of inverse square law force, like gravity is or like electrostatics is, Coulomb showed that the period of a pendulum swinging under the influence of that force would be proportional to R. You can look back at your notes for that argument, but we went through that when we covered Coulomb. So if the force, magnetic force, coming from this current carrying wire, if that force decreases, drops off with the square of the distance as Biot moves his magnetized needle further away, then you would expect, I mean, if he doubles the distance, I mean, R here, in this case, is this distance, right? From the wire to the magnetized needle. So if the force were like this, if he doubles the distance, I mean, let's say that he sets his needle swinging now, and for the strength of current he has, it swings 60 times in a minute. Okay, so the period is 1 second, right? Now, if he moves it further away, it's going to swing slower, right? Because it's not, the force is obviously going to go down as you increase the distance, which will cause it to swing more slowly. But if it followed this kind of a law, if he moves it twice as far away, it'll go, well,
Time will go down.
the period will go as the distance if the force goes inversely with the distance squared. That's what Coulomb showed. So if we have this kind of a force law, then if we double the distance, we should double the period. So if we had 1 second here, double the distance, we should get 2 seconds. Okay, well, Biot does that. He doesn't get 2 seconds. Instead, he finds that the period is more like 1.4 seconds. Sure.
Did he cancel out the magnetic force of the Earth?
Yeah, yeah. He's done what Ampere did, set magnets around to cancel out the magnetic field of the Earth. So that's not a factor here. The only magnetic force on this needle is coming from the current carrying wire. Now, so when he doubles the distance, he gets like 1.4 times for the period. Now, what does that suggest to you? Anything? Can you think of a relationship between 1.4 and 2? Is there anything you can do at 2 to get 1.4?
Subtract 0.6.
Subtract 0.6. That's one possibility. Take the square root. Absolutely. So what Biot actually finds here is that the period seems to go as the square root of the distance r. Or, I mean, another way to put that, if you don't like to think in terms of square roots, is that the period squared is proportional to r, rather than the period being proportional to r. Yes?
What's R?
Oh, r is the distance between the needle and the current carrying wire. So now remember, the whole point of this experiment is to find out how the magnetic force from this current carrying wire how the strength of that force varies with distance. Okay, so Biot has a simple approach here. He's just going to put his magnetized needle at different distances, set it swinging, and figure out how the speed of the swings varies as he varies the distance, and then he can relate that to the force. Now, I won't go through the math again, but if you go back to the law of pendulums and do something exactly parallel to what we did with Coulomb, you can prove, and Biot did, that if the force is proportional to 1 over r rather than 1 over r squared, then the period squared will be proportional to r. So I can leave that as, those of you who are mathematically inclined can go back and look at the mathematical derivation from that we did for Coulomb and see whether you can see how this follows if you follow the same sort of reasoning. But this is true. And this is what actually comes out of Biot's experiment, that when he finds experimentally this relationship between the period of swing of the magnetized needle and its distance from the current carrying wire.
Did
Troy.
anyone ever do experiments to see like magnet's repulsive force, like how it varies with distance?
Oh,
It was attractive, but anyone do repulsive?
yeah, we're going to get to that in, well, Coulomb, let me see. You're right, he just did the attractive force and assumed that the repulsive force would be the same. But, right, so no one did that. Ben.
Can you get a period squared?
Oh, well, I mean, whatever the period, what this means is, let's say that you determine a period of 2 seconds. Well, you square it, you just get 4,
Yeah.
right? So what that means is that if let's say you start out with a distance where the period is 1 second, what this formula tells you is that if you want a period of 2 seconds, you're going to have to not just double the distance, but quadruple the distance. Okay, you're going to have to move 4 times further away in order to get a period of 2 seconds. Okay? You see? Okay. Yes?
Did he do that? Like just move farther and farther and just like look at
Yeah.
get
Yeah.
perfect squares and stuff to see if it would work?
Right. I mean, he tried enough distances to, I mean, you can't convince yourself that this is what your experiment is proving unless you try a number of distances. You can't just try 2 distances or something. So I'm sure that, I don't know how many he tried, but I'm sure he must have tried 5 or 10 different distances in order to convince himself that this was the right law. Okay, so that's a good experiment. You see how these scientists always build on, what was discovered by their predecessors. I mean, he's obviously not only using Orsted's basic discovery here, but he's familiar with exactly what Coulomb did, and that gives him the idea for doing this. And you see that Now, we might be surprised by this because this is the first, this is really the outcome of his experiment. This is what he wanted to find, was how the force varied with the distance. Now, for gravity, we saw that the force falls off as the square of the distance. So as you double the distance, the force goes down by a factor of 4. So the force falls off quite quickly. And it's the same thing for electrostatics, right? If we had a big ball of electric charge and calculated how the electric force decreased as you moved away from that ball, it decreased as the square of the distance, right? This is the first force that we've seen, in fact, that didn't decrease as the square of the distance. It goes as 1 over the distance. So if you double the distance, force doesn't go down by a factor of 4, it just goes down in half. Now, Ampere and Biot, though, figured out that this wasn't actually all that surprising, because in those first 2 cases that I talked about, we were talking about the force from, say, some little mass, okay, and it was just localized in one location, okay, and then, or we had a little ball with some charge on it, okay, and we were talking about what happened, how the force decreased as you moved away. But here, we're talking about the force from a wire. Okay, it's not the same. It's not just it's not a little sphere. It's a wire that extends in one dimension. Now, the Biot and Ampere figured out, well, maybe this isn't so different as what we've seen before for magnetism and charge. What if, instead of just having a little ball of charge, let's say we have some long object and we charge it up. Okay, so there's charge everywhere on this long object. And then we talk about, as we move away from that object, how does the electrical force decrease? Well, it turns out you can show that it decreases as 1 over r. Now, it also, unfortunately, turns out that you need calculus in order to show that. So I'm not going to do that for you. But it is true. So I just wanted to make that connection between, at first it looks like we've discovered something really radically different here. A force that falls off as 1 over r rather than 1 over r squared. But it's not quite so radically different because we're really dealing with a different geometry here. A long wire as opposed to a point mass or a point charge. Okay. So, so far we have that the result of this experiment is that the force is proportional to 1 over r. Now, we're also interested in how this force varies as we vary the current, right? What do you think if we leave the magnetized needle in the same place and say we just double the the current. What do you think is going to happen to the force at the needle? Evan?
It's going to double.
That's a good guess. Turns out to be right. So it turns out that to behave exactly in the way you would expect. If we have, let's say, we're creating this current with a certain kind of battery, say a zinc oxide, a zinc silver battery, and we add another identical zinc silver battery to the circuit. Okay, well, obviously, the upshot of that is we're going to double the current, right? I mean, if one zinc silver battery produces a certain amount of current, then two ought to produce twice as much. So that's the way. I mean, they didn't have a way to actually measure current at this stage, but it was easy for them to know they had doubled it or tripled it just by doubling or tripling the battery. So they could vary the current and see exactly how that affected the speed of the swing of this needle. And what they found, let me see, in this case, he finds that T squared is proportional to 1 over the current. In other words, if he let's say he quadruples the current, okay, increases it by a factor of 4, then T will go in half. Okay, in other words, it'll start swinging twice as fast. Okay, that's what this equation means. That's what he found experimentally, and that he was able to prove implies that the force is proportional to the current. Okay, so now we can the total result of Biot's magnetic pendulum experiments with this current-carrying wire, he's proven that the force is proportional to the current and inversely proportional to the distance from the wire. Troy.
But if we have forces, that force is, oh no.
Yeah, this isn't obvious, but you have to go back to your pendulum law and work it out. Oh, what?
If F is proportional to I, then how is it also proportional to I over R?
Oh, well, I just put the two results together. F is proportional to I. F is inversely proportional to 1 over R.
Oh, okay.
This was the first result. This was the second result. We can just combine them to get this. Okay. Now, there's a in a way, of course, this is a little this is somewhat indirect because you have to go through, you have to start with the law of pendulums and then go through the math that takes you from this to this. There's another possible way that you could show the dependence of these magnetic forces on current and distance, and a more direct way that I don't think anyone actually did exactly the experiment that I'm going to describe for you, but it could be done. So, and it's I think it'll show you what in a more direct way exactly how that law that we just arrived at can be demonstrated experimentally. But instead of working with a magnetized needle this time, I want to work with 2 current-carrying wires. Okay, so let's look at the force between electric currents. And let me see, I'm going to try to do a perspective drawing for you this time because I took some heat from my bad drawings this morning. Let's say that we have again, a rectangular wire and we have it raised up off the ground on some sort of pivot so that it can tip. Okay, now let's say that we have another wire stretched underneath underneath this the wire on the right side here. Okay, and let's have the currents I'll just label this below movable wire. Okay, and let's have the currents go in the same direction here. Now, what's going to happen in this case? Ben?
They're going to repel, or what?
I mean, you can work it out if you don't remember. The
movable one will go down.
Yeah, the movable one's going to go down because if you actually, when the 2 currents are in the same direction, they attract. And you can see why that would have to be, because, let me see, if you take like the force on the movable wire, the first thing you have to do is figure out, well, what's the magnetic field direction at the location of this, the magnetic force at the location of this wire? Well, it's coming from this wire, and if you put your thumb in the direction of the fixed wire, then the field, the magnetic force from the fixed wire is going to be in this direction at the movable wire, right? So then if you put your fingers in the direction of the current and cross, then it's got to go down. again, my drawing isn't too clear, but we worked that out this morning, that if you have two currents going in the same direction, parallel currents going in the same direction, they attract. So this movable wire will be pulled down toward the fixed wire. Now let's say that we try to keep it stationary by hanging little weights on this side. We can do that. Okay, let's say we have to, I don't know, hang a 1 ounce weight on this side when we have a certain fixed current going through these wires, and they're a certain distance apart. Let's say they're well, then you can see how it'd be easy to figure out, let's say, the distance relationship, right? Because all you do is you keep the current constant, you just vary this distance, and then you figure out how much. You just hang weights until it balances, and lo and behold, you find out that if you half the distance, okay, what's going to happen? What will you have to do in terms of hanging weights on the other side in order to balance it? Neve?
And twice as many weights.
Right. Yeah, you have to double the weight in order to, if you half the distance between these wires. Troy?
Always.
And that's just because, I mean, everybody sees why that's true, because the force varies inversely with the distance. Okay, if you make this distance half what it was before, you've doubled the attractive force between the wires. So this wire is being pulled down with twice as much force. Well, if you're going to balance it, you better put twice as much weight on the other side. Troy?
Isn't this a lot like the scales thing with the electric force, and then you have the weight on the other end of the scale that they had done before?
Yeah, exactly. I mean, when people first started trying to measure the strength of electrical forces, remember, they would just take they could take a normal balance, okay, has its two trays, and if let's say you hold a charged object, remember I described holding an electrical charged object. Let's say you have a piece of glass that you've been rubbing your cat against, and it's all charged up. Well, it'll pull this plate down, right? Well, you can get a measure of the strength of that electrical force just by how much weight do you have to add over here in order to balance that out. So if you have to add 5 ounces of weight over here, then the strength of this electrical force was 5 ounces. So this is the same exact idea here. You get a measure of the strength of the force between these two currents just by how much weight you have to hang on the other side. And you can go through, again, varying the distance here, and you find that it obeys exactly this law. If you double the distance, the force goes down in half. And of course, you can do the same thing now. You can keep the distance constant and vary the current just by adding in more batteries. See. And again, you find that it varies just the way Biot's original pendulum experiment showed. So you get that exact same relationship that Biot showed with the magnetic pendulum. Okay? So this is the start of actually finding the mathematical laws behind this new effect that Oersted had stumbled across in a class demonstration. Okay. Well, let me, there's a, that's about all that I wanted to say about Ampere. He was the one that took Oersted's original discovery and realized that the magnetic forces around a current-carrying wire were circular, and then established these that all electric currents exert forces on all other electric currents, and how that worked. Came up with those two handy right-hand rules, and then started to actually find the work out the math behind this and show that the forces were proportional to current and inversely proportional to distance. So that's a lot for one guy to do, and he did that really within a few years of Oersted's discovery. Now the next guy that we're going to cover is not French, he's English, and you might have heard of him, Michael Faraday. Has anyone heard of him? Okay, he's one of the greatest experimental physicists, maybe the greatest in all of history. So oh, oops. Does that look better? Let me see. His years are 1791 to 1867. And Faraday, I'll just give you a brief introduction to him today. He was the son of a blacksmith who was, a poor manual laborer, born in London, and not really given much of an opportunity for a formal education. So you wouldn't think that this was a promising start for a great scientist. But at the age of 13, he was apprenticed to a bookbinder. So he was supposed to, the idea was Faraday would study under this guy for a few years, and then he would become a bookbinder, make books. Well, the one great advantage this gave Faraday was he was surrounded by books. He didn't particularly like the idea of spending the rest of his life binding books, but he liked the opportunity to read them. And he, starting at the age of 13, he started reading encyclopedias, reading all the chemistry books he could find because he was fascinated by chemistry. And by the time he was in his late teens, he had decided that what he really wanted to do was become a scientist. Now, this is, I mean, in most countries throughout all of history, it would have been almost impossible for someone born into a family that had never done anything except manual labor to raise themselves to the level of getting becoming completely self-taught and then becoming one of the country's great scientists. But England at the time was much freer in that respect than most other countries. And Faraday actually managed to pull this off. What he did was he attended some lectures, some night lectures at the Royal Society, which was the main scientific society in England. And some of those lectures were given by a chemist named Humphrey Davy, who was one of the best chemists in all of England at the time. And Faraday was fascinated by Davy's lectures, and he took really good notes on the lectures, and then he would go home and think about them and add his own thoughts to what Davy had said in the lecture. And he ended up with this whole notebook packed full of material from Davy's chemistry lectures and Faraday's thoughts on it. And he sent his notebook to Humphrey Davy, asking for a job in his lab. And I mean, this was a pretty bold thing for a blacksmith's son to do. Well, Davy was so impressed with the notebook that he hired Faraday as his laboratory assistant when Faraday was, I think, age 20. And then within, let me see, it was within about 10 years after that, Faraday had become one of the top scientists in England. So that it's a remarkable story. And next time I'll tell you about an experiment, one of Faraday's first really famous experiments, that will give you an idea of how clever he was as an experimentalist. And it gave people insight into these forces, these electromagnetic forces, and it led to the invention of the electric motor. So, next time.